The universe has a schedule, or at least we thought it did. According to everything we knew, galaxies are supposed to take time to grow, hundreds of millions of years to gather gas, more time to form stars, even more time to become massive, structured, and bright. But then, something looked back at us. Not nearby, not recent, from a time when the universe itself was still learning how to exist. And what it showed us should not be there. Imagine opening a history book, turning to the very first page, and finding skyscrapers already standing. That is exactly what the James Webb Space Telescope is seeing. Fully formed galaxies, massive, bright, structured, appearing far too early in cosmic history. So early that by our best theories, they should not exist at all. For decades, cosmology told a clear story. After the Big Bang, the universe was simple, hot, uniform, almost boring. Matter had to slowly clump together under gravity, small clouds first, then stars, then small galaxies, only much later the giant galaxies we see today. That slow buildup is not a guess, it is built into every major model of the universe. But James Webb is showing us something else. Galaxies appearing just 300, 400, 500 million years after the Big Bang. Some with masses similar to the Milky Way, some already old, red, and chemically mature. This is not a small problem. If these observations are correct, then either galaxies formed far faster than physics allows, or our understanding of the early universe is missing something fundamental. And here's the unsettling part. James Webb was not built to find this. It was built to confirm our models, to refine them, to fill in details. Instead, it is exposing cracks, deep ones. The telescope looks deeper into space than any instrument before it. But looking deeper into space also means looking further back in time, because light takes time to travel. When James Webb observes a galaxy 13 billion light-years away, it is not seeing where that galaxy is now. It is seeing what it looked like almost 13 billion years ago. That means Webb is giving us direct snapshots of the infant universe. And the infant universe looks disturbingly grown up. Some of these galaxies are forming stars at rates that shouldn't be possible. Others appear too massive to have assembled so quickly. Some even show signs of structure, disks, bulges, organized rotation. Structure takes time. Order takes time. But time is exactly what they did not have. At first, scientists assumed it had to be a mistake. Maybe the distances were wrong. Maybe the galaxies were closer than they looked. Maybe the light was being misinterpreted. So teams across the world rechecked the data again and again and again. The results stayed the same. Different instruments, different methods, same conclusion. These galaxies are real, they are ancient, and they are far too developed for their age. One researcher described the feeling like this: it's not that one thing is off, it's that everything is off at once. Because this isn't about one strange object, it's about dozens, then hundreds, all pointing in the same direction. Something about the early universe does not match our expectations. And that raises a dangerous question. What if the timeline itself is wrong? What if galaxies didn't grow slowly, but explosively? What if gravity behaved differently in the early universe? Or worse, what if our picture of the Big Bang, the very foundation of modern cosmology, is incomplete? James Webb is not just showing us distant objects, it is showing us our assumptions. And right now, those assumptions are under pressure. Because if massive galaxies existed this early, then something accelerated their formation. Something powerful. Something we haven't accounted for. Dark matter behaving differently. Unknown physics, or processes we have never observed before. And this is only the beginning. Because the deeper Webb looks, the more of these impossible galaxies it finds. Each one a message from the past. Each one asking the same question. How did this happen so fast? And if our models are wrong about the beginning of the universe, what else might we be wrong about? Pause. Because the next clue doesn't just challenge how galaxies formed, it challenges how fast the universe itself was able to evolve. And once we follow that trail, the story becomes far more unsettling than anyone expected. To understand why these galaxies are such a problem, we need to slow down. Not the story, the physics. When astronomers talk about a galaxy's age, they don't guess. They measure light. Light carries information, its color, its intensity, its spread across wavelengths. James Webb was designed specifically to read this ancient light, especially infrared light stretched by the expansion of the universe. This stretching is called redshift. The higher the redshift, the farther back in time we are looking. Before James Webb, we could only see faint smudges at extreme redshifts, blurry hints of early galaxies. Too little detail to say much. Webb changed that overnight. Its mirrors are large enough, its instruments sensitive enough to turn those smudges into objects with shape, color, and mass. And that's where the problem appeared. When researchers measured the redshift of these galaxies, they landed at values corresponding to just a few 100 million years after the Big Bang. That alone was expected. What was not expected was what the galaxies looked like. Their brightness suggested enormous numbers of stars. Their colors suggested older stellar populations. Their mass estimates were shocking. Some appeared to contain tens of billions of stars. To put that in perspective, the Milky Way took over 10 billion years to build its current mass. Yet here were galaxies that seemed to do something similar in less than 500 million years. That's like watching a child outrun an Olympic sprinter. At first, astronomers suspected a calculation error. Mass is tricky to measure at cosmic distances. Brightness can be misleading. Dust can alter colors. So they applied corrections. They assumed extreme star formation rates. They assumed unusual stellar populations. They assumed the light might be amplified. Even after pushing every parameter to the limit, the galaxies were still too big. Some teams tried a different approach. Instead of asking how massive are these galaxies, they asked how old do their stars appear to be? Because stars age in predictable ways. Young stars burn hot and blue. Older stars glow redder and cooler. The light from these galaxies didn't look young. It looked mature, meaning stars inside them had already lived, aged, and evolved, which adds another layer to the problem. To have old stars, you need time. To have time, you need earlier star formation. To have earlier star formation, you need galaxies forming even sooner. That pushes the origin of these galaxies closer and closer to the Big Bang itself. Uncomfortably close. So close that, according to standard models, there shouldn't have been enough matter clumped together yet. Gravity works slowly on large scales, especially in the early universe when everything was expanding rapidly. The math says small structures should form first, large ones come much later. But James Webb is showing us large ones immediately. It's as if the universe skipped steps. Some researchers tried to explain this by invoking extreme efficiency. Maybe early gas clouds collapsed almost instantly. Maybe stars formed faster than ever observed. Maybe black holes played a role. But even the most aggressive scenarios struggle, because forming stars is messy. Radiation pushes gas apart. Supernovae blow material away. Star formation slows itself down. Nature puts limits on speed, and these galaxies are breaking them. One astronomer described the situation like this: "We can tweak the models, but at some point the tweaks become admissions that we don't understand the system." And this wasn't happening in one observation. It was happening across multiple surveys, multiple regions of the sky, multiple independent research teams, different galaxies, same impossible timeline. Which means this is not an outlier, it's a pattern that suggests the early universe was far more efficient, far more aggressive, and far less patient than we believed. And that raises a deeper question. If galaxies grew this fast, what was helping them? Because gravity alone may not be enough. Something else may have been amplifying structure formation. Something invisible. Something we already believe exists, but may not fully understand. And once we look at how matter itself was moving in the early universe, a disturbing possibility begins to take shape. Because these galaxies may not have formed in isolation. They may have been riding something, a cosmic current. A current that shaped the universe long before stars ever lit up the dark. And when we follow that idea, the story takes a turn that few were prepared for. To solve the mystery of these early galaxies, astronomers asked a new question. Not how big they were, not how old their stars were, but where they appeared. When researchers mapped the locations of these galaxies, they noticed something strange. They weren't evenly spread. Instead of appearing randomly across the early universe, many seemed clustered along faint filament-like regions. This immediately rang alarm bells, because the universe has a hidden structure. On the largest scales, matter is not scattered randomly. It forms an immense web, a cosmic web. Invisible filaments of dark matter stretch across space, connecting nodes where galaxies gather. These filaments act like rivers. Gas flows along them, matter accumulates at intersections, and galaxies grow fastest where flows converge. This idea wasn't new. Simulations had predicted it decades ago. But here's the problem. According to those simulations, the cosmic web should still be weak and thin at early times, too fragile to support massive galaxies so soon. Yet James Webb was seeing galaxies sitting exactly where filaments should be strongest, as if the web had formed earlier and grown faster than expected. Some scientists proposed a radical possibility. What if dark matter clumped faster in the early universe than our models predict? Dark matter makes up about 85% of all matter. It doesn't emit light, it doesn't interact with radiation, but it does interact with gravity. And gravity shapes everything. If dark matter collapsed more efficiently in the first few 100 million years, it could have built gravitational wells quickly. Deep wells, powerful wells, the kind that pull in gas at extreme rates. That gas would cool, condense, and ignite star formation on massive scales. In this scenario, galaxies didn't slowly assemble, they were fed, fueled by steady streams of matter flowing along dark filaments, a cosmic conveyor belt. But this explanation creates another problem. Because to accelerate dark matter collapse, you need new physics, something that changes how dark matter behaves. Some models suggest dark matter may interact with itself. Others suggest it may have been warmer or colder than assumed. Each possibility alters how quickly structures form, and none are confirmed. But the evidence kept pushing in this direction. Webb wasn't just seeing early galaxies, it was seeing organized early galaxies. Aligned, structured, positioned where theory says matter flows should exist. Which suggests the early universe wasn't chaotic. It was already organized, already patterned, already flowing. And that changes how we think about cosmic evolution. Because if the cosmic web emerged almost immediately after the Big Bang, then structure formation began far earlier than expected. Not gradually, but violently. Not slowly, but with momentum. Some simulations have been rerun with modified assumptions, and when dark matter behavior is altered, when initial conditions are slightly changed, suddenly galaxies like the ones Webb sees begin to appear. But those changes ripple outward. They don't just affect galaxy formation. They affect how fast the universe cooled, how radiation moved through space, how early black holes formed, how the first stars lived and died. Which means adjusting the timeline in one place forces adjustments everywhere. And that's where the discomfort grows, because cosmology is a connected system. You can't pull one thread without tugging on the rest. And the cosmic current idea raises an even deeper question. If matter was flowing so efficiently, what was driving the flow? Because gravity alone explains direction, but not speed. Something may have enhanced the motion. Something that acted in the background of the early universe. Quiet, invisible, but powerful. And that brings us to an uncomfortable possibility. The early universe may not have been governed by the same physical rules we see today. The laws may have been flexible. And if that's true, then the universe we observe now may be the calm aftermath of a far more extreme beginning. A beginning that left fingerprints in the galaxies James Webb is now revealing. And the next clue doesn't come from galaxies themselves. It comes from something far darker, something smaller, something capable of growing just as impossibly fast. Because while galaxies were forming too early, so were black holes. And their existence may be the key to understanding how the universe grew up so quickly. As astronomers struggled to explain how massive galaxies appeared so early, another discovery made the problem far worse. James Webb didn't just find galaxies, it found what lived inside them. At the centers of several early galaxies, Webb detected intense energy signatures, not from stars, but from something far more extreme: supermassive black holes. Black holes with masses equivalent to hundreds of millions, and in some cases over 1 billion times the mass of the Sun. And these black holes existed less than 500 million years after the Big Bang. This was shocking, because black holes grow slowly. Even under ideal conditions, a black hole feeding at the maximum possible rate takes hundreds of millions to billions of years to reach such enormous sizes. Yet here they were, fully formed, already dominant, already shaping their galaxies. This created a paradox. Either these black holes started growing much earlier than we think, or they grew much faster than physics allows. Neither option fits comfortably within current models. Traditionally, black holes are thought to form in stages. First, a massive star collapses. That creates a stellar mass black hole. Over time, it feeds on surrounding gas. It merges with other black holes. It grows. Slowly, patiently. But Webb's black holes don't look patient. They look rushed. Some appear to have gained their mass in a fraction of the expected time. To explain this, scientists proposed a radical idea. What if the first black holes weren't born from stars at all? What if they formed directly from collapsing clouds of gas? These are called direct collapse black holes. Instead of starting small, they begin massive, hundreds of thousands of solar masses from the very beginning. This would give them a head start. But there's a problem. Direct collapse requires very specific conditions. The gas must remain hot. It must avoid fragmenting into stars. It must collapse all at once. Those conditions were thought to be extremely rare, yet Webb is finding black holes everywhere, which suggests these conditions may not have been rare at all, and that changes everything. Because if black holes formed early and massive, they would shape their galaxies from the inside out. Their gravity would pull in gas, their energy would regulate star formation, their presence would accelerate galactic growth. In other words, the galaxies didn't create the black holes. The black holes may have created the galaxies. This reverses the traditional story of cosmic evolution. And the evidence doesn't stop there. Some of Webb's observations show black holes outshining the combined light of all the stars around them. This means they were actively feeding, consuming matter at extreme rates, releasing vast amounts of energy into space. That energy would heat surrounding gas, but also compress it in certain regions, triggering bursts of star formation. A violent cycle. Growth feeding growth, structure amplifying structure, and suddenly the impossible begins to look possible, but at a cost, because these black holes shouldn't have had enough time to form, grow, and dominate so early. Their existence implies one of three unsettling possibilities. Either time worked differently in the early universe, or matter behaved differently, or our understanding of gravity is incomplete. None of these are comfortable conclusions, but Webb keeps pointing in the same direction. The early universe was not slow, it was aggressive. Dense regions collapsed quickly, energy moved violently, structures grew fast, much faster than our equations predicted. And black holes were at the center of it all. They weren't rare anomalies, they were common. Which raises an even deeper question. If black holes formed so early and so massive, what role did they play in shaping the large-scale universe? Because black holes don't just affect nearby stars. On large scales, they influence gas flows, radiation fields, and even the temperature of the universe itself. And when many black holes exist close together, their combined influence becomes enormous. This leads to a disturbing possibility. The early universe may have been dominated not by stars, but by darkness, by invisible engines reshaping space before light had a chance to take over. And that brings us to the next revelation. Because Webb didn't just show us early galaxies and impossible black holes, it revealed something even more troubling. The light itself, the light from the early universe, doesn't behave the way it should. And that forces us to question not just how things formed, but how time itself unfolded. When James Webb began sending back its deepest images, astronomers focused on something subtle. Not the shapes of galaxies, not their size, but their light. Because light carries history. Every photon traveling through space is a message from the past. And Webb was detecting light that appeared far too evolved for how young the universe should have been. These galaxies weren't glowing like newborns. They looked mature. Their light showed signs of older stars. Stars rich in heavier elements like carbon and oxygen. But those elements don't exist at the beginning. They're forged inside stars and released when stars die. Which means for these galaxies to contain them, there must have been earlier generations of stars. Stars that lived and died. Stars that enriched their surroundings. all before the universe was even 1 billion years old. That timeline is tight, uncomfortably tight. According to standard models, the first stars, called population 3 stars, should take time to form. They should burn briefly, explode, and slowly seed the cosmos with heavier elements. But Webb's data suggests this entire cycle may have happened much faster than expected, almost immediately. Some galaxies show chemical signatures that imply multiple generations of stars, not one, not two, but several. Which raises a disturbing question: where did all that time come from? Because if the universe is only a few 100 million years old at the moment we're observing, then something accelerated the process. Either stars formed earlier, or they formed faster, or the clock itself ran differently. Astronomers examined another clue: the color of the light. Redshift. Redshift tells us how fast the universe has expanded since the light was emitted. Higher redshift means older light. Webb is detecting galaxies at extreme redshifts. Some estimates push them to redshift values above 10, even 13. That places them incredibly close to the Big Bang. Yet their light looks too complex for such an early epoch. It's like finding an ancient city with advanced infrastructure in a time period where only stone tools should exist. Something doesn't line up. One explanation is observational. Perhaps dust is affecting the light. Perhaps we're misreading the signals. Scientists tested this carefully. They compared Webb's infrared data with simulations and alternative models, and while uncertainty exists, the pattern remains. These galaxies are not primitive. They are structured, evolved, chemical-rich, which suggests the universe didn't ease into complexity. It rushed. Some physicists now wonder if the early universe expanded differently than we think. If cosmic inflation, the rapid expansion after the Big Bang, behaved in a more extreme way. Perhaps expansion slowed earlier, allowing matter to clump faster. Or perhaps density fluctuations were stronger, giving gravity a head start. Each of these ideas tweaks the timeline, but each also creates consequences, because changing expansion affects everything: galaxy spacing, cosmic background radiation, large-scale structure. And yet Webb's observations keep pushing in that direction, toward a universe that matured at breathtaking speed. Which leads to a deeply unsettling possibility. What if our timeline is correct, but our assumptions about early physics are wrong? What if energy behaved differently? What if particles interacted more strongly? What if gravity itself was stronger? These ideas sound extreme, but the light demands explanation, and the light does not lie. It traveled billions of years to reach Webb's mirror, and it's telling us the same story again and again. The universe grew up too fast, and that means something fundamental about the early cosmos is missing from our understanding. But the next clue doesn't come from light alone. It comes from something even ancient: a faint echo, a background signal, a relic of the universe's earliest moment. Because when scientists looked at that signal again, they realized it might be hiding the reason everything happened so quickly. And that brings us to the oldest light in existence. Long before the first galaxies formed, before stars ignited, before black holes began to feed, the universe left behind a signal, a faint afterglow, the cosmic microwave background. This radiation fills all of space. It is the cooled remnant of the Big Bang itself. For decades, it has been one of the strongest pillars supporting our model of the universe. It tells us how hot the universe once was, how dense it was, how smoothly matter was distributed. and until recently, it seemed to agree beautifully with our theories. But James Webb has forced scientists to look at this ancient signal again. Because if galaxies formed too early, if black holes grew too fast, then the early universe must have been less smooth than we thought. Tiny irregularities in the cosmic microwave background are what eventually grew into galaxies. Slightly denser regions pulled in matter, slightly emptier regions lost it. These differences were measured with extreme precision by missions like WMAP and Planck. And according to those measurements, the early universe was almost perfectly uniform. Almost. But almost matters, because Webb's discoveries suggest those small differences may have been more powerful than we realized. Some physicists now suspect that subtle features in the background radiation have been underestimated. Not errors, but interpretations. The data itself hasn't changed. Our reading of it has. There may have been hidden patterns, subtle correlations, tiny fluctuations that acted as seeds for rapid structure formation. If those seeds were stronger, gravity would have had more to work with. Matter would have collapsed sooner, faster, more violently. This could explain why galaxies appear mature so early. But this idea creates a tension, because the cosmic microwave background also tells us about the universe's expansion rate. And changing early structure formation means changing how fast space expanded. That leads directly to one of the biggest problems in modern cosmology: the Hubble tension. Two different methods of measuring the universe's expansion rate give two different answers. One uses the early universe, the other uses the nearby universe, and they don't agree. James Webb's discoveries may be the missing link. If the early universe evolved differently than our standard model assumes, then both measurements might be correct. They're just measuring different versions of cosmic history. This would mean the universe's expansion has not been uniform over time, that the rules themselves shifted as the cosmos cooled and matured. A dynamic universe. Not one set of laws applied forever, but phases, transitions. This idea is controversial, but it would explain why early structures appear advanced while the background radiation still looks smooth. The universe may have hidden its complexity in subtle ways only now becoming visible. And there's more. Some researchers have noticed unexpected alignments in cosmic data, large-scale patterns that shouldn't exist if the universe were perfectly random. These patterns are faint, debated, but persistent. And Webb's galaxy distributions appear to echo them, as if the early universe had a preferred structure, a direction, a flow. Which brings us back to a haunting question. Was the early universe truly random? Or was it guided by underlying forces we don't yet understand? Because if the initial conditions were not neutral, if they favored rapid structure formation, then everything we see today is the result of a universe that was primed to build, primed to organize, primed to grow complex. And that realization changes the story, because it means James Webb is not just finding strange galaxies. It is revealing that the universe may have been designed, not consciously, but physically, to evolve faster than we imagined. And the next clue takes us even deeper, because it doesn't come from light or radiation or galaxies. It comes from the absence of something, a silence, a missing population, something that should be everywhere but isn't. And that absence may be the most unsettling evidence yet. As astronomers pieced together the early universe, another mystery emerged. Not what was there, but what wasn't. According to theory, the universe should contain a vast amount of ordinary matter, atoms, gas, dust, all the stuff that makes stars, planets, and people. Yet Webb's observations hinted at something strange. Some regions of space were missing the matter we expected. Galaxies appeared in clusters, but vast stretches between them were emptier than models predicted. Not just slightly underpopulated, completely barren in ways that were hard to reconcile. This missing matter problem isn't entirely new. Astronomers had noted it before with X-ray observations of galaxy clusters. But now Webb gave a sharper, more detailed view. It could actually trace where the matter should be, and it was absent in surprising amounts. Some scientists propose this could be the influence of dark matter again. Invisible, massive, and dominant, it shapes how ordinary matter clumps. Perhaps the missing matter was already pulled into filaments and early clusters, leaving enormous voids behind. Or perhaps we've misunderstood the balance between visible and invisible matter. And here's the unsettling part. These voids, these gaps, are not random. They have structure, patterns, alignments, almost as if the universe itself has a blueprint. Could the distribution of early matter be influenced by forces we have yet to recognize? Some theorists suggest exotic physics. Unknown interactions in the early universe might have caused matter to flow preferentially into certain regions, accelerating galaxy formation and leaving vast emptiness elsewhere. And if that's true, it explains both the early massive galaxies and the missing matter. But it also raises a chilling implication. Because if the universe's matter was guided by forces beyond gravity, then our standard models of cosmology, those equations we rely on, might be missing a crucial piece of the puzzle. Something that shaped not just stars and galaxies, but the very skeleton of the cosmos itself. This opens the door to deeper questions. What dictated these flows? Why did some regions evolve so fast while others remained empty? And could we be missing other hidden patterns still waiting to be discovered? James Webb is not just revealing galaxies, it is revealing the architecture of the universe, hints of invisible currents, hidden blueprints, and forces that may have orchestrated cosmic history long before we existed to notice. And the story doesn't end here, because galaxies, black holes, and missing matter are all part of a bigger cosmic puzzle, one that may redefine how we understand time, space, and the very evolution of the universe itself. The next revelation dives into that bigger picture, where the early universe's extreme growth collides with the mysterious physics we thought we understood. By now, a pattern begins to emerge. Galaxies forming too early. Black holes growing impossibly fast. Light that is too mature. Matter that is missing. It's as if the universe had a plan, a hidden blueprint etched into its very fabric. Cosmologists began comparing Webb's observations with simulations. Not just ordinary simulations, the ones that include dark matter, radiation, and the cosmic web. Even with these sophisticated models, the early universe in Webb's images doesn't behave as expected. Clusters form where they shouldn't. Massive galaxies appear where models predict only emptiness. Black holes outpace star formation. Every anomaly points to one possibility. The universe is structured, not random, not chaotic, but organized in ways our equations barely hint at. Some researchers propose that quantum fluctuations from the Big Bang were amplified in certain regions, creating a natural bias for early structure. Others suggest interactions in dark matter, unknown forces that nudged matter into filaments faster than gravity alone. If this is true, The cosmic web itself could act as a kind of skeleton, guiding the growth of galaxies and black holes from the very first moments of existence. It's an elegant idea, and yet it's unsettling. Because if the universe was pre-structured, then our understanding of random evolution is incomplete. The laws of physics may not have been the same everywhere. The cosmos may have had preferred directions, regions designed to collapse faster, paths that funneled matter with invisible precision. This blueprint theory could reconcile Webb's discoveries. Early galaxies aligned along filaments, supermassive black holes forming almost instantly, missing matter concentrated in voids, mature light appearing too soon. It paints a picture of a universe that is both chaotic and meticulously organized. And it hints at a larger truth. Cosmic evolution is not just a story of time and gravity. It is a story of flow, structure, and unseen guidance. Even the earliest light, the cosmic microwave background, shows subtle hints of this design. Tiny temperature variations, previously dismissed as random noise, now appear to align with the very filaments Webb is detecting. It's as if the universe left a map for us, hidden in radiation, matter, and galaxies, waiting for instruments like Webb to reveal it. But this realization comes with tension. If the early universe was structured, then some of our most basic assumptions are challenged. About how quickly stars form, about how galaxies evolve, about the balance between dark matter and visible matter. And if the universe has this underlying architecture, then we may only be scratching the surface of the cosmic design. The next part of our journey examines the forces that may have shaped this blueprint, from the smallest particles to the largest filaments. And it forces us to confront a truly staggering possibility: that the universe had intent, not conscious, but physical, guiding its growth from the very beginning. If the universe truly had a hidden blueprint, then something must have guided matter along its earliest paths. Gravity alone can't explain everything we see. Galaxies appear too massive, black holes grow too fast, light matures too soon. Astronomers began looking at other forces. One candidate is dark matter, the invisible glue of the cosmos. It outweighs ordinary matter by almost 5 times. It interacts through gravity, but possibly through other, subtler forces we haven't yet detected. Another candidate is dark energy, the mysterious force accelerating the universe's expansion. If dark energy fluctuated in strength early on, it could have pushed and pulled matter, speeding structure formation in some regions while leaving voids in others. Some theorists explore the role of primordial magnetic fields. Weak, invisible threads of magnetism could have channeled gas and dust, directing flows of material into the earliest galaxies. Then there's a more radical idea: interactions beyond known physics. Perhaps the universe allowed particles to behave differently in its first few 100 million years. Perhaps energy transfer, particle collisions, or even gravity itself operated in a slightly altered way. All of these forces, known and unknown, could work together to sculpt the cosmic web, to guide galaxies along filaments, to feed black holes, to enrich light with complex elements almost immediately after the Big Bang. This framework is not fully proven, but it aligns with Webb's observations in remarkable ways. It also suggests that the universe is far more dynamic than we imagined. Not a slow, uniform expansion, but a living, flowing system, with matter and energy moving with intent. And here's the most unsettling consequence. If these forces were active early, then the universe we see today is only the aftermath of a far more violent and structured youth. The patterns Webb detects, the rapid growth, the alignment of galaxies, the massive black holes, all hint at a hidden order beneath the apparent chaos. And if that's true, it forces us to reconsider our place in the cosmos. We are not just observing a universe unfolding randomly. We are witnessing the result of forces operating on unimaginable scales. Invisible currents guiding the evolution of all matter, from the smallest star to the largest galaxy cluster. The next part takes us even deeper, examining what this blueprint could mean for the future of the universe and how it might reshape our understanding of cosmic destiny. If the universe's early structure was guided by hidden forces, then the story of its future may also be shaped by these same principles. James Webb's discoveries not only reveal the past, they hint at how cosmic evolution might continue. The massive black holes and early galaxies suggest that the universe's growth is far from random. It follows patterns, flows, currents. Consider the cosmic web. Galaxies are not isolated. They form along vast filaments of matter, stretching across hundreds of millions of light years. These filaments connect galaxy clusters, creating a scaffolding that dictates where galaxies can grow, merge, and evolve. If this scaffolding exists now, it existed in some form billions of years ago, guiding the formation of the first galaxies. And if forces like dark matter, dark energy, or magnetic fields are involved, then these structures are dynamic, not static. They continue to shape the universe even today. Another implication comes from supermassive black holes. Their growth and energy output influence star formation and galaxy evolution. Webb shows us that these black holes were active early, driving violent cycles of gas inflow and outflow. This suggests the universe is self-regulating. Regions that might have collapsed too quickly are moderated by feedback from black holes. Areas that might have remained empty are seeded with energy to spark star formation. It's a cosmic dance, chaotic yet ordered, random yet guided. And what does this mean for the ultimate fate of the universe? Traditional models propose scenarios like the Big Freeze, the Big Crunch, or the Big Rip. But if the universe's evolution is influenced by hidden forces or a cosmic blueprint, then these outcomes might be far more complex than we imagine. The growth of galaxies, the expansion of space, and the interactions of matter may follow subtle rules we have yet to discover. Webb's observations suggest that early structure formation was not only faster than predicted, but possibly more deterministic. This could mean that the universe's destiny is, in part, written into its very fabric. And here's a deeper, unsettling thought. If the universe is structured at such a fundamental level, then the laws of physics may not be uniform across all scales and times. Regions that formed early may behave differently from those that form later. Even the flow of time in extreme environments could be influenced by these forces. James Webb is showing us that the universe is a living system, not in a conscious sense, but in how matter, energy, and forces interact in complex, organized ways. Galaxies are not just points of light. They are evidence of a dynamic, evolving network that has been shaping itself since the dawn of time. And as we continue to peer deeper with Webb and future instruments, we may uncover even more extreme galaxies, black holes, and cosmic flows. For each discovery, the universe challenges our understanding, pushing the boundaries of physics, cosmology, and our imagination. The universe is not a quiet, slow place. It is vibrant, aggressive, and intricate, and our early observations are only scratching the surface.